Okay, so today we want to discuss a process known as localization. We're going to talk about the specific case of localizing an integral domain, and essentially what we want to do is give every non-zero element a multiplicative inverse. So we want to take our integral domain and embed it into a larger field so that the field contains our integral domain as a subring, and in this way, each non-zero element will get a multiplicative inverse. The prototypical example of this is the creation of Q, the, the, the rational numbers from the integers. So we take z, the integer z, and we embed it into our field Q under some kind of construction in terms of creating these rational these pairs of numbers that we denote a over b, and with an equivalence relation on these pairs of numbers. This process is going to be generalized to just general integral domains, but you could, of course, generalize this even more to what is known as localization. And localization takes place, usually it takes place in the complement of prime ideals, um, and it takes place with any multiplicatively closed subset. That's what we require for the general case, a multiplicatively closed subset, and we can localize away from that subset. So to state it more properly, we're going to let R be an integral domain. We want to construct a field, which we'll call K of R, that contains R as a subring. This datum contains all of the information that we said before. By containing R as a subring, we have, in essence, given every element of R a, a multiplicative inverse. We want this field to satisfy a universal property. So we want K of R to satisfy the property that for all fields L and all injective ring homomorphisms from R to L, there exists a unique ring homomorphism. Well, this would be a field homomorphism from K of R to L, such that the following diagram commutes. This J we will define um, later on. So essentially what we want three pieces of information. We have our integral domain R. We want some mapping. Actually, before we have the mapping, we have our integral domain R, and we have our field K of R, and we want some mapping J that maps R into K of R such that J is injective. Then our pair K, we can call it J K of R, is satisfies this universal property. And we could phrase this in terms of more categorical language. So in categorical language, we can construct this kind of ambient category. So we consider the category C, whose objects are pairs, J, comma L. So they're pairs where J is a morphism, L is a field, and J is a ring homomorphism from R into L. That's injective, and so we have these pairs. I should have called this something else. We can call it alpha. Right, so we have these pairs. So this is an object. And a morphism of between two objects is going to be diagrams. And it's going to be a diagram. So we have one object here, and this is another object. And we have a morphism between these objects is a field homomorphism, phi, that makes the diagram commute, such that the diagram commutes. So that, of course, that means that we have phi composed with J1, that's equal to J2. And that's those are the morphisms. And our claim is that the pair that we defined before, that whatever this field of fractions is going to be, and this injective ring homomorphism J into the field of fractions, our claim is that this is initial in this category. But first we have to construct the field of fractions and understand what it is. So to construct K of R, we're going to consider the set R cross R set minus the 0 element. So essentially all we're doing is we're taking pairs of elements, where the first entry can be any element of our ring, including 0, or of our integral domain, and the second element can be any element but 0. And we're going to define, so just to refresh our memory, we bring this down here, R cross R set minus 0. What is that going to be equal to as a set? As a set, this is going to be equal to all pairs of elements A comma R, such that A and R are in R, and R is not equal to 0. And we're going to define an equivalence relation on these pairs. So we say that the pair A comma R is related to the pair A prime comma R prime if and only if A prime A R prime minus A prime R is equal to 0. So we have A R prime is equal to A prime R. And this may seem a little strange, a strange way of defining an equivalence, but we keep in mind that because this is based off of the the integers, taking integers and then constructing fractions, right? We can't just construct fractions directly from the integers, right? Because we have things like a half, like 1 over 2, that's somehow equal to 2 over 4. If we think about this in concrete terms, um, if we have two objects, half of the two objects is one object. But if we have 4 objects, half of the objects are 2 objects. So essentially, somehow these are representing the same quantity, the same ratios, and we need to um, impose some conditions so that we have a half is equal to 2/4 is equal to 3/6 is equal to 4/8. So we have to impose some conditions to make sure that we have these fractions are equivalent. And we know that a fraction, A over R, is equal to A prime over R prime if and only if A R prime is equal to A prime R. So we do this cross multiplying, this cross multiplication operation, and we get that this is true if and only if A R prime is equal to A prime R, which is exactly the type of equivalence relation we're imposing here. So now our proposition is that our relation tilde, that's what we're calling it, tilde, is an equivalence relation. And if we recall, we have to check that tilde is symmetric, or actually we could do reflexive first, that's how it's usually put, is reflexive. So A comma R is related to A comma R. We want to check that it's symmetric. So A comma R is related to A prime comma R prime is the same as A prime R prime being related to A comma R. And lastly, we want to check that tilde is transitive. If A R is related to A prime R prime and A prime R prime is related to A double prime R double prime, then AR is related to A double prime R double prime. So these are the 3 conditions that we have to check to make sure that tilde is an equivalence relation. On that front, we can see that tilde is is reflexive, right? That's trivial because AR being related to itself implies that AR, through our definition of the equivalence relation, um, that AR minus AR, of course, is 0. Um, and we have symmetry, right? If we have AR is related to A prime R prime, then AR prime is equal to A prime R by definition of the equivalence relation. And um, A prime R prime being related to AR implies that A prime R is equal to AR prime. And we know that equality is the standard, the prototypical equivalence relation, so that it is indeed symmetric. So we could swap these around and we get the conditions that we need. Now, transitivity can be seen as follows. It's a little more difficult to see, but it's not too bad. So we're going to suppose that we have A R is related to A prime R prime, and um, A prime R prime is related to A prime double prime R double prime, right? So then from these conditions, we get that AR prime minus A prime R is equal to 0, and we have A prime R double prime minus A double prime R prime is equal to 0. Now, we're going to do some manipulations here. So we're going to multiply this left equation by R double prime, right? So we multiply our left equation here by R double prime, and we multiply the right equation by R, right? And then we add these two equations together. So we have R double prime A R prime minus R double prime A prime R plus R A prime R double prime minus R A double prime R prime. And then we perform the standard manipulations. So we're going to just rearrange terms, manipulating things, canceling things out. And then we obtain R prime times R double prime A minus R A double prime is equal to 0. Now, we know that R prime, we know that that's not equal to 0, because if we recall from our definition over here, um, we have the second factor is being pulled from a pool of elements from the integral domain that's not 0, right? So we don't have to worry about this being 0, but because we're in an integral domain, this implies, since this product is 0, this implies that R double prime A minus R A double prime is equal to 0, which is precisely the condition that A R is related to A double prime R double prime. So we see that this is indeed transitive. Now, the next thing that we need to do, so we've constructed this set, right? We have this set R cross R set minus 0. So we have this as a set. We define an equivalence relation on this set, right? And the next thing that we want to do is define an algebra on the set. We want to put um, arithmetic on the set and some algebra on the set. And to do that, we are going to look at the quotient. So we're going to take this set R cross R set minus 0, and we're going to mod out by this equivalence relation, and then define operations on this to turn it into a field. So we're going to denote the equivalence class of A comma R. We're going to so here we're just letting K of R be equal to R cross R set minus 0. Right, so here I should have written this better, but here what we're doing is we're just saying that K of R, so we're taking our equivalence, we're taking our set R cross R set minus the 0, and then we're modding out by our equivalence relation. So now we're looking at the set of equivalence classes. So I'll put that here. Looking at set of equivalence classes. That's what we're doing here. And we're going to denote the equivalence class of A comma R. So one of these pairs, and we're going to denote it by the symbol A over R. So this is where we get our standard. This is following in practice with what we do when we perform this construction on the integers, right? When we take the field of fractions of Z, we get Q, and in Q things are written as A over R as ratio of integers. We're going to define addition and multiplication in K of R in the standard way. So we have A over R plus A prime over R prime. That's going to be A R prime plus A prime R over R r prime. So this is just the same as taking a equivalent to. So this is equivalent to finding a common denominator in simple um, arithmetic with fractions, and we define multiplication the same way we just multiply straight across. These operations are well defined. It's not too easy. It's not too difficult to show, so we'll just leave that for you guys to check if you'd like to. Our big claim is that under these operations, K of R is a field. The associativity of addition, that's pretty trivial as I note here. Um, we can just see that so we have if we have a over r plus a prime over r prime plus a double prime over r double prime, right? What's that going to be? Well, that's going to be equal to a r prime plus a prime r over r prime plus a double prime r double prime. I don't know, I'm running out of space here. But you can check this as well. It's not that difficult. The associativity is essentially inherited from the associativity in the integral domain. Um, Now, the important bits here are the class. So the equivalence class of 0 over 1 is the additive identity. And we can see that from 0 over 1 plus a over r, that's going to be 0r plus a over r times 1, which is going to be a over 1. Um, it should read a over r. That was a mistype. It should read a over r. Um, Commutativity, the commutativity of the addition is also a simple check, and the additive inverse of an element a over r is minus a over r, and we can see that here. So a over r plus minus a over r is equal to ar minus ar, which is going to be 0 over r times r, which is right. So this is, we have to remember, this is in the equivalence class 0 over 1. So there are many representatives. 0 over r for any element r, any non-zero element is in this equivalence class. So here we've shown that um, this additive identity is in the equivalence class of that when we add these together, we get an element in the equivalence class of 0 over 1, which is exactly what we wanted to show. Now for multiplication, the unity element is the class of 1 over 1, and the multiplicative inverse of a over r is r over a, provided that a is non-zero. And this jives with our regular definition because we know that the zero element, is non-invertible. So we could see that a over r times r over a, that's equal to ar over ar, and we want to show that this is in the equivalence class 1, 1. Right, so this is if we're writing this in terms of the equivalence class, this is the equivalence class 1 over 1. But we know that AR minus AR is equal to 0, right? So that it indeed shows us that that this is indeed the case, because if we recall, when we take we're looking at actually AR times 1 minus AR times 1. And that's going to be equal to just AR minus AR. That's equal to 0. So therefore, we do have that AR, the pair AR, comma AR, or the fraction AR over AR, this equivalence class is actually the equivalence class of 1, 1. And commutativity, okay, so we have to check commutativity. We know that every non-zero element's invertible. Multiplication is associative. It's inherited from the associativity of the integral domain, associativity of multiplication. As I said, every element's invertible, and commutativity is also inherited from the integral domain. So we have K of R as a field. if you would like more detail on that, I encourage you to go over the proofs of these on your own. They're very one-line proofs. Now we're going to get to the showing that this is actually a this is a universal construction. So we're going to define the function I that maps R into K of R by R, and we're going to send it to R over 1. And we see that this is injective for if we have I of R equal to I of R prime, then R over 1 minus R prime over 1 um, is equal to 0. What that implies that R minus, so here, right, so we have I of R is equal to I of R prime by assumption. This implies that I of R minus I of R prime is equal to 0, which implies this, which implies that R minus R prime over 1 is equal to 0, but this is only possible if R is equal to R prime. So we have I as an injective morphism, and it's a ring homomorphism trivially. And we could just do a simple proof here. So we have I of R plus R prime is equal to R plus R prime over 1, which is equal to R over 1 plus R prime over 1. And that, of course, is equal to I of R plus I of R prime. So it's an injective ring homomorphism. So the last thing we have to show is that, so we have our injective ring homomorphism from the previous definition, and this is from the previous construction. So we have these two elements, these two objects, kind of these objects. This pair is an object in our category, and we have to show that it is initial with respect to injective mappings from R embedding R into L. So for any field L. So we have to show that there exists a unique morphism, K of R into L, or K of R, well, I guess you could say uh, K of R mapping to L such that the diagram commutes. So if phi were to exist, we know that it must be a ring homomorphism or a morphism of fields. So what does that mean? That means that for all elements A over R in K of R, we must have that phi of A over R. Well, that's going to be the same as phi of A over 1 plus times 1 over R, which is the same as phi of A over 1 times R over 1 inverse, right? Because we know that the inverse of 1 over R is just 1 R over 1. So if it was a morphism, so if it was a ring hom, this would be the case. So we'd have phi of A over 1 times phi of R over 1 inverse. But we know that if the diagram were to commute, then we must have that phi composed with I that has to be equal to j. But that implies that we must have phi of A over 1, and we know that from here, A over 1, that's actually just I of A, and this is I of R. So this is phi composed with, that has to be equal to j of A times j of R inverse. So because this loosely proves uniqueness, by the hand-wavy argument, you could prove uniqueness through the traditional way of showing that something's unique, but through the hand-wavy argument that this definition is forced by the diagram, this must be unique, and this must be the only way that we can define this mapping. So we're going to define phi that takes A over R, and it's going to map it to J of A, J of R inverse. So we have to show that this is a well-defined ring morphism. So if we have two equivalence classes in K of R, so if we have A of R, A comma R is similar to A prime comma R prime, we must show that phi of A over R is equal to phi of A prime over R prime. Um, but we have that A R prime is equal to A prime R. So J of A R prime is equal to J of A prime R, since of course J is a well-defined morphism, a well-defined field morphism. This implies that J of A, and we can break it up into this way because it's a ring homomorphism. Um, so phi is well defined, right? So this all comes from the fact that J. This all comes from the fact that J is well defined, and we're working in a field. So phi is well defined. Now, given A over R and A prime over R prime, we have that sum. So we're going to check here. We're checking that phi is a homomorphism. So we have phi of A over R plus A prime over R prime. We sum these together, and we get J, when we apply phi, we get J of A R prime plus A prime R times J of R prime inverse. And then we do some algebraic manipulations, and we obtain that phi of A over R plus phi of A prime over R prime is equal to phi of A over R plus A prime over R prime. And by similar algebraic manipulations, we see that this is a ring homomorphism. So we have A over R times A prime over R prime, right? That's going to be phi of A prime over R prime, which is equal to J of A prime, J of R prime, which is equal to J of A, J of A prime, J of R, J of R prime, and the rest is just trivial from there by rearranging the terms, and we get everything that we need. So this is indeed, oops, this should be inverse, and this should be inverse here, and there should be an inverse here. By rearranging the terms, we could see that this is indeed a ring homomorphism. So this shows that the pair I comma k of r is initial, as we wanted to prove in the first place.